All right, today we are diving into some really cool research that could totally change where and how we use AI. It's a technique called relaxed quantization, and it's all about one big fascinating idea: teaching artificial intelligence to think small.
Right now, when you think of the really powerful AI, the kind that can create stunning images or have a real conversation, you're thinking about these huge models that live in giant data centers. They need an incredible amount of power and memory to do their thing. But imagine this. What if we could take all that brain power and shrink it way, way down? What if it could run not on some remote server farm, but right here, in your pocket, on the devices you use every single day? Now that's the goal. Okay, so to make that dream a reality, we've got a pretty fundamental problem to solve first. How on earth do you cram a giant AI brain, one that was built for a supercomputer, into the tiny little chip inside your phone or your watch? So, the real hurdle here is getting these massive AI models to work on what researchers call resource constrained devices. And that's just a fancy way of saying things like our phones, drones, or those smart gadgets we have at home. These things just don't have the juice, the battery life, or the raw horsepower to run the kind of AI we're used to in the cloud. The go-to trick for this is a technique called quantization. The basic idea is pretty simple. You compress the AI model by basically making its numbers less precise. So instead of using super detailed numbers, you use simpler ones. And this makes the model way smaller, faster, and much easier on the battery, perfect for a small device. But there's a catch. And trust me, it is a big one. This simple act of rounding the numbers creates something we can call the rounding cliff problem. At its core, quantization is really just a fancy form of rounding. You're taking a super precise number and just snapping it to the nearest simple value. I mean, it seems totally logical, right? But for an AI that's actively trying to learn, this sudden snapping action is a complete disaster. The researchers put it like this: the discontinuity makes gradient-based optimization infeasible. So, what on earth does that mean in plain English? Well, gradient-based optimization is just the technical term for how most AIs learn. They make tiny, tiny adjustments and see if things get better. The problem is that word discontinuity. Let's imagine the AI is trying to find the lowest point in a valley. It learns by taking tiny steps, feeling for which way is downhill. But with rounding, the ground is totally flat everywhere, with these sudden, sheer cliffs. Think about it. If a number changes just a tiny bit from 3.1 to 3.2, the rounding number stays stuck at 3. There's no slope, no gradient. The AI gets absolutely no feedback on which way to go. It's basically learning with a blindfold on, and the whole process just grinds to a halt. And this is where relaxed quantization comes in to save the day. It's a seriously clever and elegant way to get around that rounding cliff. So here's the absolute key idea. Instead of forcing a number to be exactly 3, relaxed quantization says, well, it's probably 3, but, it also has a little chance of being 2 or maybe 4. It cleverly swaps that hard, absolute decision for a smooth landscape of probabilities. Okay, you really gotta look closely at this slide because it shows the whole idea in action. On the left, you've got the input value, that little black star. Now, instead of this rounding it, the algorithm treats it as the center of a smooth bell curve, a whole range of possibilities. Then, and you see this on the right, it uses that curve to figure out the exact probability of that value landing on each of the nearby target points. The beautiful part is that this whole process is smooth. It's continuous. It gives the AI that gentle slope it needs to follow, which is exactly what it needs to learn. So the whole process breaks down into these 4 steps. First, you set up your target values, that simple grid you want everything to snap to. Then, you model your input number, not as one single point, but as that smooth curve we just saw. You use that curve to figure out the probabilities for each target. And then finally, you use this special smooth sampling method to actually pick a value. This gives the AI the gentle feedback it needs to learn, completely avoiding that cliff. So look, the theory is brilliant, no doubt about it. But does it actually work when the rubber meets the road? Let's check out the results. Wow, this image just says it all, doesn't it? What we're looking at are charts of the model's internal numbers, its weights, after it's been trained. Those vertical dashed lines, those are the simple target values. And just look at that. The weights have naturally learned to group themselves into these perfect, tight clusters right around those targets. The learning process itself has guided the model to become easy to compress. It's not fighting the system, it's working with it.
And this just underscores why it's so important to quantize the entire model. The paper points out this staggering fact. For a pretty common AI model, if you leave just the very first layer at full precision, it can demand 2.5 times more computational work than quantizing the whole thing. To be truly efficient, you have to go all in. Now, this chart shows how relaxed quantization stacks up against everybody else. It's plotting model error versus how much computation it needs, so the best models are going to be in that bottom left corner. And the black triangles, those are the RQ methods, they're sitting right on what's called the Pareto frontier. You can think of that as the absolute edge of what's possible. It means they're achieving the best possible accuracy for the lowest possible cost. And if we just zoom in on a head-to-head comparison, say a 5-bit model, the advantage is crystal clear. Simple rounding has a pretty bad error rate, almost 37%. Another popular method gets it down to about 35.4%. But relaxed quantization comes out on top with the lowest error rate of them all. So it's not just more efficient, it's actually more accurate too. So what's the big picture here? What does this all add up to? Well, it points to a future where AI isn't just powerful, but it's also incredibly, unbelievably efficient. So let's just quickly recap. The big problem was that simple rounding creates that mathematical cliff that just stops an AI from learning. The solution, relaxed quantization, brilliantly smooths out that cliff using probability, giving the AI a gentle slope to follow. The result, we get highly efficient and accurate AI models small enough to run on our everyday gadgets. And the impact? Well, it paves the way for powerful AI to be truly everywhere. And that just leaves us with this one last incredible question to think about. This kind of tech brings us a huge step closer to a world where every single device we own has the power of a supercomputer. So when that day finally comes, what amazing new problems are we going to solve?